Hello, it's Keith here, and this is lesson 31 of the simple series of my 650 assembly programming tutorials, and we're looking at sprite clipping again. We drew a graphic on the screen of the PC Engine last time using the Tilemap, but this time we're using the hardware sprites. And of course the benefit of this is we have a lovely smooth scrolling and our sprite can go off the screen on all sides. Now our chibi code graphic today is 48 by 48 pixels and the PC Engine hardware sprites are 16 by 16 pixels. So we're using 3 by 3 hardware sprites to make the graphic today, and we're cropping them and removing them as they're no longer needed on the screen. So if our chibi code goes almost entirely off the screen, we're not going to use any unneeded hardware sprites to draw it. We're going to remove them. Now we're not going to discuss the logical units and the theory of the cropping so much this time. I'll go into it where needed, but if you need to know more about that, please see the first half of the last Simple Series episode where I discussed that in a great amount of detail that I really don't want to repeat if I don't have to. Anyway, let's go over to the source code and let's see the source code of today's example. Okay, so the source code today is in a lot of places quite similar to last time because a lot of the code has just been tweaked slightly with regards to the cropping, but the code that actually draws the graphic to the screen is very different because of course we're dealing with hardware sprites now. So the first thing I just need to briefly cover is the routine that actually gets the graphics onto the screen. So we've got this draw player routine which we had last time, which draws the chibi code graphic to the screen, but there is also now a clear unused sprites routine and a update sprites routine. Now what are these? Well, if we have our chibi code graphic and we go off the screen, the number of hardware sprites needed will start to go down, and this could cause a problem if we don't remove the unneeded ones. So if I just remove the clear unused sprites routine and run again, well, now when our chibi code graphics on the screen everything looks fine, but as we start to go off the screen we're leaving a mess, and these are the sprites that are no longer needed that haven't been removed from the screen. When the chibi code comes back on the screen they're reallocated to used sprites and then they disappear again, but once again they will be left lying around. So that's what that clear unused sprites is doing. Update sprites is actually transferring the VRAM cache to the sprite table. Now when we define a sprite in VRAM, that isn't enough to get it on the screen. We need to transfer them via DMA to the actual graphics. So if we just have a quick look at that. So it's a very simple routine here. We just run this sequence here. Now the VRAM table is at 7F00, that's the definitions of the sprites, and we're using function 13 in hexadecimal to update the SATB, which is the sprite table as it actually defines the hardware sprite settings. That's how we update the sprite VRAM. But the clear unused sprite routine is very simple. All we're doing is we're loading the hardware sprite number and we're setting all of the hardware sprites to a position off screen, and we're updating, we're continuing until we've done all 64 hardware sprites, starting from the last used one in hardware sprite number. Now hardware sprite number needs to be zeroed at the start of our routine, and you can see that happening just there, and then our draw player routine is being called. Now our draw player routine has changed a little bit. The size of our sprite is still the same in logical units because logical units are always converted to whatever they need to be, as is the X and Y position. However, the graphic we're using for the first pattern is now different because these are in a different format. As always, all of the graphics in my tutorials are exported with my free AccuSprite editor. It's free and open source. You can download it from my website. And we've just used a different export function to export the graphics in the format needed for the hardware sprites rather than the tile pattern data. So that's what we're doing there. And we've got the VRAM address of the first pattern there. And we've got our do crop routine, which has changed, and we'll have a look at that now. So our do crop routine. So as before, our do crop routine is calculating the conversion from logical units into physical ones, and it's also handling if the sprite is entirely off the screen, in which case we set the carry and return. Now there is a slight difference in the way it works on this system for hardware sprites and the other systems. Now normally when we return, the X and Y coordinates are converted into pixels or tiles or something like that. Now they aren't in this case, and the reason for this is because we've got a screen that's 256 pixels wide, but we actually need to deal with some negative values for sprites that are almost entirely off the left-hand side of the screen. For example, we need to cope with positions like that, and that's actually outside of a 0 to 256 range. The visible screen in sprite coordinates, in these hardware sprite coordinates, is 64 down and 32 across, is the actual top corner of the screen, which would be the very first pixel up here. So we need to actually cope with that, and so we're sticking to logical units for our X and Y coordinate, but we're converting our height and our width into a number of sprites. So that's a slight difference from the usual code to what we've done here. Also, if you compare this to things like the Super Nintendo example, they were working in 8 by 8 pixel sprites, but this one works in 16 by 16 pixel sprites. So again, you're going to see some differences for that, but the rest of the code hasn't really changed that much. So as before, we're zeroing the Y register, which stays 0 throughout, zeroing the sprite H clip, and D and E, which are our temporary variables. We're then loading the Y position, subtracting the minimum visible Y position in logical units, and if that hasn't caused any overflow, then there's nothing to do, but if it has, we need to calculate the amount to crop. So we're negating, comparing to the height of the sprite, and if it's the entire sprite, we're giving up. Otherwise, we're storing the amount we need to crop in E here. Now, this is the number of sprites we're going to need to remove, or it'll be converted into a number of sprites later, but there's a problem. As we remove sprites, we need to change our Y coordinate to make our movement smooth, even though big chunks of the sprite are disappearing. And so what we do here is we are masking out the bottom 3 bits, which are a fraction of a hardware sprite. That's a number from 0 to 8 in pairs of pixels, so 0 to 16 in pixels, which is 1 sprite's worth, and we're EORing that to convert and allow the sprite to move smoothly as parts of it are removed as we go off the top of the screen. If you remove these lines, then it will jump jerkily and it won't be very nice. So that's what those are doing there. We're then storing the new Y position here, and then we're adding the height. We're comparing to the height of the screen in logical units, and if anything needs to be cropping, we're converting it to a number of sprites and storing that in D, unless it's the entire height of the sprite, in which case we're giving up again. As I say, very similar to last time, it's just these conversions really for the fact that we're working in 16 pixel hardware sprites this time. Okay, so we're now converting, adding the amount removed from the top and the bottom, negating it and adding it to the height of the sprite, and then we're converting that into a number of sprites again, and because we're working in 16 pixel sprites, we're storing that new height there. If we are removing anything from the top of the sprite, then we need to change the first sprite number. So we're just calculating how many patterns we need to skip to remove that, and so we're converting here into a number of sprites. Here we're rounding up there a bit, and we're storing the number of sprites to remove in X. We're then calculating the number of patterns in each logical unit here. We're actually doubling it up here because rather strangely the value in IY that we have to store in VRAM for the pattern number, we have to increment twice for each actual hardware sprite, which is a bit weird, but that's what we have to do. So we're doing that here. There's actually one logical shift right missing here almost to cope with that. And then we're just updating IY, the IY pair here. This is a simple multiplication to remove any patterns that we need to skip because our sprite is partially off the top of the screen. So that's what we're doing there. So we've done the vertical axis there, and now we're going to do the horizontal one. We're resetting our DE temporary variables here in the 0 page, and we're loading the X position here, and we're subtracting the minimum X position in logical units. If that's caused an overflow, then we're negating it, we're rounding up a bit, and we're storing the amount to remove in ZE here, and then again we're flipping the bottom bits and we are storing that new X position, and again that's to allow for smooth movements on the left hand side of the screen as we're removing chunks of our sprite as we go. So that's updated the X position, and we now need to add the width and see if we need to remove anything from the right. And so here we're calculating the new width, and we're taking the amount removed from the left, adding the amount removed from the right, and we're masking that into a number of sprites, and we're shifting that to the right twice, calculating the number of patterns that we need to skip if our sprite is on the left or the right, because we're going to need to skip some of the patterns after each of the lines has been drawn onto the screen. So we're doing that here, and we're storing that in sprite H clip. What we're now doing here is we're shifting that back and we're updating the width of the sprite here. Now once we've done that, the final thing we need to do is remove anything on the left hand side. So we're removing the amount to remove on the left, shifting to the right to convert it into a number of patterns, and then we're adding that to the IY pair, and that's again to cope with the fact that if our sprite is at the far left, we need to skip some of the patterns before we start drawing. We're then converting the width and the height into a number of sprites by divided by 8, which is effectively calculating the number of 16 pixel sprites, because each logical unit that we've been working in this whole time is 2 pixels. So there we go. So that's the it's a quick summary of how we're doing the cropping there. I've gone through that a little bit quicker. If If you need to see more detail on that, please see the last episode where I went into it in more detail. But it's basically, as I say, the same code, just with some conversions for the fact that we're working in hardware sprites. So that's how we get our cropping done. How do we actually draw these hardware sprites? Well, it's all pretty simple, really. So we've got our X position here. We've got our hardware sprite number, which will start as 0. And we then select our hardware sprite address at the 7F00 range in VRAM. We are then incrementing our hardware sprite by 4 bytes here for the next memory address for next time. Selecting we want to write some data. And then what we need to do is we need to take our X and Y position and convert those into a pixel position, because, as I say, the first visible pixel in the hardware sprite range is at 32 across and 64 down, and that's going to mean that our 256 by 224, I think it is, the size screen will not fit within a byte once we add that coordinate. So we're going to use the IX pair to cope with that and allow for the 16-bit values. So here we're zeroing the IXH, we're loading our Y position, adding 24, and the reason we're adding 24 is we need to have our sprites almost entirely off the top of the screen. So we've got basically one entire 16 pixel sprite invisible. Now 64 minus 16, but we're working in logical units, which are pairs of pixels, so 64 minus 16 divided by 2 is 24. So we're adding that to our Y position, and then we're shifting to the left, effectively multiplying all of that by 2, and that now gives us our low byte, and then we're updating the high byte as required. This is now the correct Y position for this one of our hardware sprites. So what we're doing here is we are then transferring this Y position in 16-bit to the VRAM, and that's defining the Y position of this hardware sprite. What we're then doing is the same for the X position. So we're zeroing IXH. We are then transferring X, which is the offset, because we're going to have to draw up to 3 sprites across the screen to draw our Chibico. And so our X is our offset here, and it's going to go up by 1 each sprite. Now this is in multiples of 16. So what we're doing is we're shifting this X position to the left 3 times, effectively multiplying it by 8. We're then adding our X position from the B, which was calculated by the cropping routine in logical units, and we're updating our high byte as necessary, but this is still now in logical units, which is multiples of 8. So we shift again to the left one more time, and that's now in pixels. And so we then add 16 here, and the reason we're adding 16 is because the starting coordinate is 32 across, but again we've got one hardware sprite entirely off the screen so that we can do our cropping. And so 32 minus 16 is of course 16, so we're adding our 16 there. And then we've now got our 16-bit pair for the X position. We're writing those into VRAM here. Okay, so we've now got our X and Y position for this hardware sprite. We're then using IY, which is our pattern data. We're storing that. And we're then storing our attributes, which is 0 in this case. We're not using any hardware attributes, any sprite attributes here. We're then incrementing the IY pair twice here. The reason we're doing that is because we need to update it by 2 each time. The patterns aren't in the same units as the hardware sprites. We update it twice each time. We are then incrementing our X count here, and that is the number of hardware sprites on this line. We're then comparing to the width of the line, and we're repeating as needed. Now that X will have gone up by 1 for next time, and that's why we are transferring X to A here and multiplying it up by 8 before adding our X position as calculated by the cropping routine. So by the time we get to this point, we've done one entire line of our sprite, our Chibico graphic, but there are multiple lines. So we're adding 8 logical units, which is 16 pixels of course, to our Y position, and then we are doing any cropping, because remember, if our sprite is off the left hand side of the screen or the right hand side of the screen, we need to remove some sprites before the next line. So we're adding the sprite H clip to our IY pair here. We're then decreasing our height count and repeating until we're done here, and so that repeat will jump up to the top here, and we'll recalculate all of the hardware sprite number and select the VRAM address as required to do that. So it's a bit of a pain, but it's not too bad, and it does create a fairly decent effect. So there we go. Now, if you like what you've seen, you can go to my website, download the source code, and download the build scripts and all the other stuff as always. And as I always say, if you manage to make something amazing out of the source code today, you're welcome to use it in whatever you want. Even if you somehow manage to use it commercially, I don't care. You're welcome to use it. Good luck to you. I hope you get some benefit from it. And if you've liked what you've seen, please like the video because it encourages me to keep making more videos. I've been making videos today for hours, and I spend all of my weeks writing source code and writing content on the website for videos, so it would really help me out if you do that. And if you would subscribe as well, you will benefit because you will see the next video that I do on the PC Engine. Anyway, I hope you've enjoyed this today. Thanks for watching, and goodbye.